Hello everyone, I'm Wirwit Riopas. I'm going to give a presentation of my senior project, a corner-based Saliency model. The previous name is Improving Computational Model for Visual Saliency on Single Image. The presentation will begin with an introduction where I will give a brief background about a Saliency model and its types, and I also review some past works. Then I am going to present the proposed model in detail. And the final section is results, which I will describe evaluation metrics and some experimental results. A Saliency model. To understand this, we need to know a visual attention. When we see a scene, we receive massive amount of information. It is inefficient to scan each pixel like a computer. So we have a mechanism that selects important areas for further processing, and in the scene, we usually look at layers. In the scene, at faces, or an object. We need to find a way to represent this mechanism in a machine. So given an input image, we need to find or predict human fixations. But it is impossible to know exactly where human look, and we use Saliency map that allows some error to predict this. It is a grayscale image that determines how important each pixel is. An algorithm that do this is called Saliency model. There are two types of Saliency model. Top-down, where we look is affected by our current goal. For example, while we're searching for an apple, we are looking more at red and round objects. And bottom-up model, which conspicuous objects attract us to look at it. The proposed model is bottom-up. The three most common bottom-up features are intensity, color, and orientation. In this section, I will describe the proposed model in detail. Intensity, colors, and orientations are encoded along early visual pathway, beginning at retina through primary visual cortex, or V1. Normally, biological-based bottom-up models such as ET's model extract conspicuity by three features to create a Saliency map. But the proposed model uses corner feature, which is extracted in upper stages of visual processing. There are three stages in our model. First, image representation, where an input image is separated in intensity and color channels. And the second stage is the core of algorithm, where we obtain corners by first applying Gabor filters at 4 orientations, then multiply them together pixel-wise. At the last stage, we normalize and sum together the corner maps from intensity and color channels. The complete implementation detail can be viewed at this link. At first stage, an input image is separated into 6 channels, 2 for intensity and 4 for color. We can think of it as a color space for our visual system. For an example, this input image is separated into 6 channels. At corner extraction stage, we first extract orientation features by convolving each channel with Gabor filters for both real and imaginary parts. Then we combine real and imaginary parts by root of sum square, and it is called Gabor energy filter. These are 6 channels from the previous stage. To visualize, we extract orientation from intensity on channel. To extract corner, we directly multiply different orientations together. Do this for every channel. Corner feature maps are very sparse. We can enhance by logarithm function. Then, in the last stage, we promote individual clusters by subtract each pixel from the average of surrounding. Then, we suppress sprawling information by dividing with number of local peaks. Finally, we combine each channel together. The first column is input. The second column is recorded from human. The Saliency maps by our model is at the last column. In this section, I will briefly describe an evaluation metric. Then we show the result and end this section with discussion. The metric we use is called area under receiver operating characteristics. Basically, we calculate true positive and false positive rates at every possible threshold. Then plot a curve between them. An area under this curve is the score. A final blurring on Saliency map usually increases the AUC score. So we can calculate AUC score at different blurring. The model was tested on Toronto dataset. It contains 120 indoor and outdoor images. This is the result comparing with other models. Notice how bigger sigma of Gaussian initially increases the score and then reach optimal value and then fall down. Our model is competitive. The overall performance by average from the previous curve and the optimal value. This is an example of Saliency maps from different algorithms, and the proposed model is at the last column. Our model is also tested on MIT Saliency benchmark. It ranks 16 from 58 models. So why do we use corner? You can see that it is harder to recognize an object in the last column, where corners are removed. Moreover, given a figure or an object, corners are its boundary, and we usually look at the center of an object. So corners are useful to predict those areas. The weaknesses of our model is that there is no orientational pop-outs. Usually other models can determine orientational conspicuous items, just like at the center. But our model does not have this mechanism. Second, our model is sensitive to final blurring, so it is hard to find the right parameter for a dataset for an optimal performance. The strengths of our model are, first, it is based on human visual system, so it is consistent. There are also some evidence of the corner encoding at later visual stage. Second, it is extensible for more complex features like shape, text, face, and others. For example, a circle can be generalized as dots along a circular path. Even visual illusion of a circle can be encoded in the same way. In the case of lines, beginning and ending contain most information because it essentially determines the length of a line. We don't spend time depends linearly on how long the line is. We look at the beginning, then quickly moves to its ending. For a face, in this photo, corners show how important our eyes, nose, and mouth are. Thank you for watching.